Today we'll have part 3 of the bootcamp on machine learning by Challenger Mishra. So, Challenger, please. Thanks.
Thanks very much for the opportunity to speak with this panel of experts, really, in theoretical physics, pure mathematics. It's been fantastic to be able to speak with you over the last week and a half. And I'm very excited about this final talk, and I hope I can leave you with some interesting messages by the end of this talk. So I understand this is perhaps I'm talking to the survivors of this week. It's late on Friday evening, so I appreciate those who have come to join. Without further ado, I'll begin, but I'll also again keep it as interactive as it can possibly be. So today I will I'll sort of summarize at the beginning what we have been doing so far in this bootcamp, and take you through one example of one interactive example of working with mathematical data using machine learning. And please interrupt me and ask questions as often as you'd like. I'd shared some data with the organizers, with Suresh, a few hours ago. So in case you have that, then you can code alongside, or if not, I can share the data with you individually later, as well as the mathematical notebook which we will use. So let me begin. So in the first talk, we sort of addressed the question of how to generate interesting questions in the context of mathematics with the aid of machine learning. And we were inspired by Hilbert's list of 23 problems from the 1900s. And in particular, we spoke a little bit about the 13th problem, and which is rather easy to state, and it relates to a representation of solutions to degree 7 equations of polynomials as a composition of a finite number of 2-variable algebraic or continuous functions. As I was mentioning in my previous, in my first talk, that this, an attempt to resolving this conjecture by Hilbert resulted in a powerful representation theorem in the 1950s, a la Kolmogorov and Arnold. And not only that, that representation theorem posited a new view of geometry, which is different from the smooth view of geometry that mathematicians were familiar with until that point, at least in a wide-ranging scenario. And to make things more interesting, in the 80s, this representation theorem saw new light in the context of neurocomputing, and helped firmly establish that neurocomputing was indeed on the right mathematical trajectory, or had the right mathematical underpinnings. And Heck Nielsen, who built the special types of neural networks, which are 2-layer neural networks, based on the representation theorem that went into solving or resolving part of Hilbert's 13th problem, had actually built these networks, and that we spoke about in the first talk. We spoke a little bit about mathematical inequalities. And we understood that mathematical inequalities can form a particular class of mathematical results which have wide-ranging applications, and primarily from its ability to bound functions in mathematics. And this kind of a relationship between functions has ubiquitous applications, so they appear everywhere. And around around 100 years ago, a large number of inequalities that existed or were conjectured were collected by Hardy, Littlewood, and Polya, and published with the Cambridge University Press. And although they had collected such inequalities, it wasn't ultimately clear why such an endeavor was taken up by the authors in the first place. In fact, they sort of mention in the preface of their book that it is often really difficult to trace the origin of a familiar inequality. It is quite likely to occur first as an auxiliary proposition, often without an explicit statement. And therefore, they sort of decided to collect all the inequalities that they possibly could and under one umbrella. But in this book, this book, which we only found in hindsight whilst working on our framework of generating conjectures based on inequalities, was quite an interesting find. So we realized that these inequalities, within the context of continuous real-valued multivariate functions, actually form a well-defined class of mathematical objects that we can characterize through geometry. We realized that these inequalities form this interesting space, which we call a conjecture space, and we in the first lecture we saw an embedding of this conjecture space in some space of relations. And just to give you state of the art on what's happening in this sector, we sort of have a refined definition of the conjecture space, or rather really an equivalent and a simpler definition of conjecture space from our original work, which I have highlighted in this slide. So effectively, a point on the conjecture space is a continuous function that is well defined on a compact subset D of real numbers, or Rm in particular, such that the function that the point represents always dominates the zero line, or is always dominated by the zero line. So this is our space of conjectures. We looked at group actions on this space, and we spoke in some detail about what kind of groups can act on this space. And we had also touched upon what kind of other structures might this conjecture space have. And rather interestingly, we found that the conjecture space is itself a group. And not just that, given the fact that we had already shown this is a topological space, we realized that this is a topological group. So the conjecture space is a group under pointwise multiplication of functions. And further, recently we have realized that there is a second group that acts on this space, or a better way of putting it is the conjecture space admits a group action by a set of bijective functions which form a group under multiplication, under composition. So the conjecture space admits this group action by this group under both multiplication as well as function composition. And as an illustration of this general setup, the picture on the left shows you an overarching space of relations, and within that is embedded a space of conjectures. Initially, we had thought that it might be possible, it might be difficult to talk about the conjecture space as an algebraic variety, but later we realized that this might indeed be the case. And when such a thing happens, we might be able to characterize the space fully, or to a very large extent, by understanding its symmetries and using tools from classical invariant theory. And the kind of tools that were developed last century, or last century, by Emmy Noether are very useful in computing invariance of this space under various group actions, and we'll report on this pipeline as it progresses. Finally, all these geometric insights prompted us to write down an oracle that takes as input some mathematical functions, amongst which you might expect some relations, and utilize machine learning to effectively solve a sampling problem, and upon which you end up generating mathematical conjectures, which are valid on a as large an amount of data as you are able to work with. And we sort of realized that this is rather interesting, and the whole endeavor has two aspects. One is we can utilize machine learning to exploit the structure of this conjecture space and generate new conjectures or new theorems, and we can work with the group actions to generate even more conjectures which are connected on the orbits of the group action. And so later we also realized that the structure of the space is rather interesting to us, and although we cannot fully characterize the space immediately, we have identified some interesting questions in this sector. So, for instance, at the moment, our setup is although we exploit the setup to generate actual new conjectures and, as previously mentioned, actual new theorems, we can do even better if we specialize the class of functions that we are talking about, and if we write down specific metrics on this space of conjectures. There are some other interesting aspects of this pipeline that we got to discuss in the first lecture, and those had to do with the goodness of conjectures, or the interestingness of a conjecture. So, meaning that when we use this framework as an organizational principle for mathematical inequalities and exploit machine learning to obtain such inequality conjectures, we should be guided by the fact that not everything might be interesting. Not everything, every point on the space might be interesting. So it is important to determine where are the good conjectures on the space, or where are the interesting ones. Now, for starters, goodness and interestingness are rather subjective sounding quantities. However, we exploited and took some and understood some of the thoughts that string theorist Robert Digraph has explained in one of his articles, and some of the interesting ideas there relate to expectations that match a physicist's understanding of what is good or interesting, meaning a good conjecture is perhaps simple in some fashion. This is something that can be characterized or made explicit. A good conjecture is therefore terse. Robert Digraph also tells us of some other criteria that is known to mathematicians. So, for instance, conjectures that can connect disjointed fields of mathematics can be rather interesting. And a fantastic example of this is monstrous moonshine. Such conjectures are absolutely outrageous, in the words of John Conway, and worth looking for. And what we are currently trying to do with this framework is to quantify exactly this. So some of my PhD students and myself and some other collaborators are working on finding such measures. And interestingly, we see the mathematical discovery pipeline as a two-stage process. One is to identify excellent conjectures, and the second step, which is potentially much harder, is to prove them. And however, these two steps might ultimately talk to each other and help us and inform us about good conjectures on the conjecture space, and simultaneously give us some insights into provability of these statements. And these are questions that some of these questions have been looked at over the last several decades by many experts, such as Mike Douglas. And we feel that with this framework that we have posited, it merits another line of investigation. So, thanks for allowing me to summarize the first lecture, which was rather theory motivated, and the second lecture was quite interesting and interactive, and we were able to write down a toy machine learning algorithm that sort of demonstrates how a real-world task, such as handwriting recognition, can be accomplished using a very small number of lines of code on Mathematica, which has all these wonderful functionalities. On that, so I had shared that notebook with our organizers. If you would like to play with that, please feel free, or if you have questions, reach out to me, please. So today, the main thing I wanted to emphasize is how to work with mathematical data using machine learning. And there are a number of things to point out here, coming from recent literature in understanding algorithmic data in the context of deep learning. So please feel free to interrupt me and ask as many questions as you'd like, and we can proceed. So the example I thought we could work with is that of finite simple groups. Sorry, just a quick aside. This was a visual summary of the first lecture, or our initial approach, and was generated by organizers of a workshop earlier this year at Oberwolfach, and it was a fantastic place to visit, and I encourage all of you to do so if you haven't. I felt it was a mathematical monastery. The case study we will be looking at today is that of finite simple groups. And so let me introduce my partners in crime here. So Yang-Hui He, whom you have interacted with during the course of this workshop, is an AI mathematician himself, and he interestingly he loves groups, and amongst other things, and he had written a paper with Min-Hyung Kim on learning algebraic structures, or machine learning algebraic structures, and trying to find interesting mathematical results through that endeavor. And they had looked at various group theoretical questions. Vishnu Chichala, he's a theoretical physicist and known to many in this audience. And one of my students from Oxford a few years ago, Max Sharnoff, who was an undergraduate computer scientist when we started this project, we sort of came together to study finite simple groups using machine learning. Now, the question of interest was the determination of a criteria for the simplicity of a group. So a a simple group is a group that has no non-trivial normal subgroups. A full characterization of finite simple groups was a very long and important endeavor in pure mathematics, and it took several decades, or perhaps even around a century, to accomplish the full classification of finite simple groups. And it led to very many interesting discoveries in the context of group theory, and a full classification is now known. And there are many interesting finite simple groups, or families of finite simple groups. And one important thing about them is that they are two-generated, meaning a finite simple group can be generated by two group elements. So Yang had suggested a very interesting setup for this problem. He suggested that let's look at the symmetric group of degree n. And from there, we randomly pick two generators or two elements. And then we forget about the parent symmetric group, but we use those generators to generate a free group, and then ask the question, does this free group have a non-trivial normal subgroup? This is a computationally intensive process, and it will lead to a deterministic outcome of whether or not the group generated by these two generators is indeed simple. But we wanted to bypass all of this, and so we decided to formulate a classification problem where we pretended that we do not know much about properties of simple groups. We simply think that simple groups are the primes of groups, meaning they can be used to generate various interesting all other groups that are finite. So we decided to set up a classification problem where the inputs are classification problem guided by a neural network, where the inputs are two group elements, or rather two permutation matrices, in fact, and the output is a simple binary yes or no. Yes representing that indeed the resulting group is a simple group, and no meaning no, it's got a non-trivial normal subgroup and it cannot be a simple group. Is this setup more or less clear to people in the audience? If not, please do ask questions. I'll pause here for a moment before I bring up the Mathematica notebook.
Just carry on. Just carry on.
All right. So I'm going to stop sharing and switch to Mathematica. Can you see my screen?
Yes.
All right, great. Also, I do apologize for my background. By some turn of fate, I am in a garage, but not held against my will. All right. So right.
Yep.
Yes.
Yeah, you did not share this notebook, right?
No, I have not, but I did share the data. Perhaps it's
the data. Yeah, the data. Yeah.
I can quickly do that actually, in case. if you drop me an email address, I can send, or I can send it to Suresh. Sorry, I should have done this before, but here it is. All right. So, to emphasize how this approach is different from the previous approach of conjecture generation that I had emphasized in the first lecture, we'll note that this is an approach where which is which has found many interesting applications through the work of Yang and other collaborators, and this approach is more or less along the lines of, you have some mathematical data that you are able to generate or compute easily or with loads of effort, and you sort of compress this information by allowing a neural architecture or maybe even some other machine learning paradigms to learn this mathematical data or properties to the best possible extent, and then attempting to interpret what the outcome has been. And the idea is that through this interpretation, through these investigations, you're able to determine a key mathematical outcome that relates to the property you are trying to understand. Here, the property of interest is that of simplicity of a group. The groups we are talking about are subgroups of Sn, Sn being the symmetric group of order n, and the question we had sort of asked in our work, and I'll share the mathematical result after going through this notebook, was that if we supply two generators, can we find the answer to the question, is the resulting group simple or not? And Max, who was only a first or second year undergraduate computer scientist at that time, did fantastic work with his machine learning skills, and allowed the first part of the pipeline to take shape. So one aspect of this pipeline is generation of data, and often you'll find that software like Mathematica might have lots of high-level functionalities, but you might have to resort to other means to generating, or other specialized software to working with specific kinds of mathematics. So in this case, since we're working with groups, we decided to work with this package called, or rather this formal algebra system called GAP, Groups, Algorithms, and Programming. It is a very useful resource. Not only do you learn a lot about groups, but you can compute a large number of things relating to groups and their properties. So it's a very interesting setup, and lots of functionalities are involved. However, what we require for the purpose of this investigation, or rather what we required us to compute some quote unquote pedestrian properties of some subgroups of symmetric groups. So what are those properties? So the properties we considered are listed here, But first, let me make this a little more readable, perhaps. Right. Yes. So let me highlight this thing. Sorry. Yeah. So the properties of interest are as follows. First of all, we are considering symmetric groups Sn. And these groups are interesting in their own right, and there are many interesting questions about these groups and very many interesting properties. So one of the parameters that is of interest to us is the order n, which is you don't need a software to compute this. You just know what it is. We also wanted to figure out if in the process of, in order to generate our data, we need a method of determining whether a group is simple. Now, if we want to do this in bulk, for a large number of cases, we need good functionalities that can tell us quickly if a group is simple, and and GAP provides all these functionalities. So is simple is a query you can make about a group to GAP, and it will give you a true or a false answer. Is abelian is another property, another functionality that GAP has, and it doesn't require an explanation, but it effectively tells you whether the group you're studying is abelian or not. Now, since we are in the symmetric representation of a group, we can talk about things like the trace and determinants of group elements. So trace of sigma 1 and trace of sigma 2. So as I was previously stating, so we study generators of groups, and we try to determine from their description alone whether a group is simple or not. And this is the question we had posed to a neural network, but that's not the experiment we are going to do here, because because through Max's work we realized that that requires a lot of data massaging, and training those networks can be time intensive. So it's probably not appropriate for a session like this. But you can read our. We can talk. I can talk about those experiments if you ask me questions, or I can share our work with you. So what these generators that we are studying, we denote by sigma 1 and sigma 2. So in effect, what we are saying is we have got sigma 1 and sigma 2 to come from the set that is represented by the symmetric set, that is a set of permutation matrices. So we choose sigma 1 and sigma 2 at random, and we can query GAP, or otherwise we can compute the traces of these matrices. We can also compute determinants of these matrices. Now, interestingly, for permutation matrices, that is the signature of the matrix. So it's either plus or minus 1. The other kind of data we collected was the order of the group that is generated by sigma 1 and sigma 2. So in other words, we construct this group that we can loosely define as being generated by sigma 1 and sigma 2. And we ask the question, is this group simple? Now, we also collect some other kinds of data about this group. Namely, we collect the order of all the group elements of G. So we collect this information. Let's denote order by O and G, where G is coming from capital G. So that those are the element orders. So we generate this kind of a data set for our purposes today, and I mean, this is a very simple piece of code that one can write in Gap. I'll work with the outcome of that Gap code and spare you Gap coding for now, although the syntax is quite nice and intuitive. So I encourage you to work with Gap because of all these interesting functionalities and ability to really probe interesting groups. So one of the files that I have shared with our organizers is this file called simple data. So let's see what that looks like. Right. Sorry, I quickly need to import some functionality. Just bear with me a second. This will make the viewing experience much better. All right, we're back. So this is what the data looks like. So let's go through it. So I've written this key that I'll copy in on top of this. So if you correlate, what this says is the first entry in our data set that we have generated using Gap is the order n. So the first entry seems to be coming from S3. So n is 3. And here we look at these two permutation matrices together, and these are our sigma 1 and sigma 2, and we generate this group G with this, and the answer to the question, is G simple, is expressed by this digit 1, meaning yes, it is simple. We also check, is it a billion? Yes, it turns out to be a billion. And if you look at these two quantities, they are the traces of these two matrices, and the following two quantities denote the determinants of these two matrices. The group that we generate contains 6 elements, so that's denoted by 6 here, and the elements have orders which are this 1, 2, 3, 2, 3, 2. We know various interesting factoids about the relationship of the order of the elements with the order of the group, and so although we will not use this data, it is interesting to mention this for the following reason. So it turns out that you can characterize finite simple groups using the order of the group and the order of the group elements completely. So meaning this information is an information about a simple group with the elements being of such and such order, and if there was another group which exhibited similar properties, we can say that they have a relationship between the two, namely they're probably isomorphic. All right, so this is the data. This is what the data might look like. Now you might wonder what this looks like, in bulk. So let's take a random sample of this data. We're actually going to do that in the next step anyway. So here, the first 10 data points all relate to S3. So we don't want that. We want diversity of data in our machine learning pipeline so that machine learning can actually capture what's happening in general terms. But even within this class of S3, we find that there are at least two different groups at play here. The way we choose the generators is at random. For small degrees, we generate a full list. But as you can imagine, as you keep increasing n, it becomes more and more memory intensive to actually store all these representations. So in our data set, orders up to 5 or 6 are fully appear in the data set, but orders above them, and we only go up to 10, we generate some amount of data for them at random. Sorry, was there a question?
No.
All right. So let's continue. So if you remember our example from the last time, we had determined that it is important to obtain some amount of data that's sort of representative of the underlying mathematics. So in that spirit, we will take a sample of size 6,000 here. In some other settings, you might be more constrained and you might not be able to generate this amount of data. But for the purposes of this example, we are lucky and we can generate. In fact, you will find that as opposed to real world data, mathematical data is cheap, and it's relatively easier to determine in many situations. But just to give you a scale of what the sizes of this data set and the sample set are, the data set is of size 8,757. This number doesn't really mean anything. It's the number of samples we have generated. And in our machine learning pipeline, we're going to work with a large chunk of this data. Now, one interesting question is, why is this? What is the correct amount of training data to use? In the presence of a certain amount of data, and one comes up with various empirical rules about, we should work with 80% of the data set and then have 10% of the data for validation, and the remaining 10 to test, etc. I don't think that is seriously important, especially for the purposes of this talk. And it is not atypical to be working with around 80% of the data or so. There is a difference in machine learning applications in a real world setting as opposed to a mathematical setting. So one interesting thing is that pertains to generalization. Now, if you are able to determine, if you're able to use 80% of the data, per se, in a real world setting, and utilize the rest to test how generalizable your model is, that metric is very important. So, because when you're deploying it in a real world setting, you want to make sure that your model is indeed generalizable. In the context of mathematics, it's slightly different. It is actually often not a bad idea to use all the data, and for the following reason. The reason being that once the goal here is to formulate some conjectures, and if you do find a conjecture, it would only help if you used as much data as you might possibly have. And the reason is that the formulation of the conjecture is this important part of the mathematical discovery pipeline. And if you are able to resolve the conjecture or prove it using some means, then in hindsight, it didn't matter how much data, what percentage of the data you actually ended up using. So so these considerations are interesting to think about in the context of mathematical data and machine learning, especially given the fact that mathematicians or applied mathematicians, theoretical physicists are widely embracing machine learning in the current day. So let's look at what are the an inference task. So in the first task, let me go back and find out what the key is. Yes. This sort of will help us remind ourselves what properties we are choosing to work with. So the first inference task I want to set up here is the following. We want to determine whether, given some properties of the generators, a neural network is able to determine whether the resulting group is simple or not. So for starters, let's work with only a handful of properties, namely the traces and determinants of the generators. So let's remove this. We keep this index n. So that's the first entry, first column. Then we keep the traces of the generators, and we keep the determinants of the generators, and we remove everything else. So these will be our inputs, and the outputs will be the second column, which is the property of simplicity. So let's have a look what this looks like. So the first entry seems to have come from S5, and the generators have traces 0 and 2 respectively, and they seem to be permutation matrices of opposite signs. If any, well, I mean, it's a 50-50 chance of this being a simple group without any further considerations. But all right, it turns out to be a simple group. In this case, let's take another one to be more explicit about inputs and outputs. And here again, we have stumbled upon another group that's simple. Now we consider this third one, where it turns out that with these properties, the group turns out to be non-simple. Now, this is not to say that these 5 properties are the sole determinant of the property of simplicity. Here, we are trying to determine some interesting criteria for the simplicity based on these properties, which is a different thing to say. All right. Now, in the spirit of the last lecture, we look at this architecture, which we take to be 3 linear layers with activations that are logistic sigmoid. And again, to emphasize from last lecture, this the architecture is not unique, and you might have other architectures that will give you interesting results. Here we follow a typical machine learning pipeline where one can play with different architectures and look at your validation set, not the test set, but the validation set, to determine what is the simplest model that explains your data. So in effect, you're implementing Occam's razor, but for the purposes of doing this within a finite amount of time, we won't be repeating those exercises, but they are rather important. So for now, we'll work with a architecture that potentially gives us half-decent answers without much experimentation. So in fact, it is highly likely that one of you might be able to come up with an even better architecture that explains the data even better, or gives you new insights that we haven't found. So I definitely encourage you to work with this. So let's build this network. Now, why did we choose logistic sigmoid? Perhaps merits an explanation. So let's look at what this activation function looks like. Oops. This is what this activation looks like. And it sort of approaches either 0 or 1 in these in the two limits of x going to -infinity and +infinity. And we also use this as a final layer. So therefore the output is something that is between 0 and 1. Now, we are trying to answer a binary question here, which is, is the group simple or not? For our purposes, we have determined that 0 denotes that it is, so this binary answer effectively captures the property of simplicity of this group. So when our machine learning architecture outputs anything above 0.5, we say that it goes to the answer is 1, and otherwise the answer is 0. I want to correct myself about the interpretation I gave earlier. My apologies, but 0 in our case denotes a simple group, and 1 denotes it is not. This choice doesn't really matter, but for the sake of consistency, I'm just clarifying. So here, again, to reiterate, as an output by the neural network that is less than 0.5 is considered to have determined that the resulting group is simple, and an output that is greater than 0.5 is determined otherwise. And it determines that the resulting group is not simple, right? So let's train our network now. Are there any questions?
Hello. Yeah, I mean, can you just give like a very quick explanation of so how this net chain functioning Mathematica works? Like, so I think you put the layer, then you put the activation and stuff, but can you just explain it a bit?
Yes, absolutely. So so effectively, so let's also use the fact that Mathematica has really nice manuals on these things. So effectively, it helps you build a chain of function operations that successively work on a given input. So and there's very many interesting functions that you can put here. So perhaps a better way to illustrate this is through this other functionality called net graph, which is you can use it in a similar fashion. So here, if you look closely, you'll find that it's an analogous way of defining things. Let me increase the size of this so you can see slightly better. Yes. So here, for example, in this instance, there seems to be a linear layer, which is effectively denoting if a matrix multiplication by a matrix of an appropriate size on a vector of inputs that you will provide. Those inputs are things that are not specified here because they are determined by your data or the kind of outcomes you want. So the architecture effectively represents a composition of layers of functions. So yes.
I just wanted to say, so then in this net chain, you don't have to specify if the layer is linear. You just put the number, like the size, I think.
Yes. Apologies, I should have made inconsistency. I think it's the same thing. Yeah.
Okay.
So
thank you. It's good.
All right. The number here just denotes the number of neurons you will have. In this example, it is just 2. In our example, it is 1,000.
Okay, thanks.
Thank you for the question. It's sort of useful to be able to determine some ballpark region in which you might want to place your number of parameters. And there's an immense amount of literature that you will find in the machine learning community that talks about this kind of issues. There are even attempts at automatically finding good architectures for your problem. And there's the differentiable architecture search that one can use as well, which can automatically determine what kind of architecture will work very well with your data. And a lot of the technology that has been developed in machine learning over the past decades, and particularly in the past decade or so, we're sort of only beginning to explore those things in the context of mathematical data. So it's worth looking into a lot of this literature surrounding what kind of architecture can best help explain your data and give you a generalizable model or help you generate conjectures and so on. Typically, one starts with, I mean, at least in my experience, it has been that, so our motivation might be solving or attempting to explain a particular mathematical or physical question, or even a theoretical machine learning question. It's interesting to play with mathematical data in a given setting and play around with the architectures and observe the outcomes. Because here we are using around 6,000 data points. So our architecture, for example, if we only had a handful of neurons and only 2-3 layers, then and we tried to explain the data using that, then that would certainly fail. However, if we allowed the network to have a very large number of parameters, then then we have some hope of capturing the mathematical property of simplicity here. So hence sort of we're going with 1,000 neurons or order of 100 neurons in various layers, and I explained why we are using the sigmoid activation function. So all right, so let's train. So what you're seeing here is again an application of Mathematica that bypasses a lot of very many important parts of machine learning. Choice of your batch size, your choice of optimizer, and we are allowing Mathematica to choose this itself. And this is not what you should do in a real world setting or in a real problem. You should have as much control as possible, and Mathematica certainly allows you to have a lot of that control. So while it trains, maybe let me show you some of the options that are available here. So these are some of the parameters that you can specify in Mathematica. You can specify, the batch size, and as I was explaining in my last lecture, effectively you have an optimization problem that involves minimization of your loss function, and the loss function effectively is a sum of squares of how many terms. The number of terms is given by the amount of data you give. If you have 10,000 data points, 10,000 sum of squares. But the optimization problem is not solved by pure gradient descent, because that might not work, and it might be computationally too burdensome. So the standard practice is to use a stochastic optimization algorithm, so that you have any hope at all of solving something like an or probabilistically solving a hard problem. So the batch size determines the number of sum of squares you will consider at a given time, and that can be 1. That can be the full set, or anything in between. And there are important studies that tell you how generalization corresponds to this choice. Learning rate is sort of something that's easy to explain. It's sort of when you're taking a gradient descent step, you can move along with a certain magnitude, and you can control that. There are no set values for any of these things, and it really depends on the context of your problem. So here we are letting Mathematica choose some of these options. Another interesting aspect is initialization itself. So there are very many interesting articles written about the importance of initialization, and they sort of can have a huge amount of say in your ultimate outcome, and so on and so forth. All right. So our network is trained, and this is what it looks like. I mean, it looks exactly like that. You can't really see the parameter values, but you can certainly import all sorts of information by querying Mathematica about this network. Typically, the weight values and bias vectors, they look rather ugly, and it's showing them would be showing you a random bunch of numbers which do not make any sense. So let's look at the outcome. So as I was saying before, given the sigmoid activation, we sort of determine that any output below 0.5 is taken to determine a simple group, and any outcome above 0.5 determines that your group is not simple. So what we do is this net has now been instantiated through the act of training. So it's no longer a function class prior to training, but rather its weights and biases have been specified, and so therefore it is a function through which you are passing your inputs. This functionality allows us to allow the network to work on all the inputs that we are interested in at the moment, which namely those that come from the training set. So here we're going to measure how well it does on the training set. So we're determining the predictions on the various inputs. Right, it has determined, but before we give you metrics for accuracies and stuff, let's also look at what the first input was, perhaps, and the first output. So so the first input was where these properties of the order of the symmetric group, the traces of the two generators, and the determinants of the two generators, and the outcome was 1. And as mentioned previously, this actually shows that the group corresponding to this is actually not simple. And apologies again, because I had made the opposite comment, so I was correcting myself. So this right. So now imagine we pass these inputs through our trained network, and it gives us this. So this is above 0.5. So we round it off and we get 1. So for the case of the first example, it seems to tell us that indeed it is doing the right thing, and it's determining the right outcome. But let's look at all possible outcomes on the training set and determine what the net accuracy here is, where we define net accuracy to be simply the number of cases it determines accurately, or rather correctly. Although I will mention here, accuracy is not a good metric here, because if we look closely at our data set, and look at the distribution of simple and non-simple groups, it turns out that in our sample of 5,000, of 6,000, only 1,000 of them were simple, and 5,000 of them were not. So the data set is quite imbalanced. So therefore, accuracy is not a good metric, and this can be exemplified in the following way. Imagine you only had 10 simple groups here, and and you had the remaining examples were non-simple, and if your network always predicted non-simple, it will be extremely accurate. It will be accurate to almost 100%, with almost 100% accuracy. Therefore, accuracy is not a good metric here. A good metric here, or rather a better metric here, is something called an F-score. It's sort of it gives you some notions of class accuracies, and you work with your predictions on different classes. How well you're determining different classes. But again, that's also not a perfect measure, because it sort of is dependent on which way you define your classes. But there are very many measures for our purposes. Accuracy and F-scores or class accuracies are kind of good enough. All right. So it turns out that in the vast majority of cases, the algorithm, this trained network is able to determine whether a group is simple or not from this property alone. In fact, these are decent accuracies. Let's also compute some mean square error, and it's also decent, and we can also determine these class accuracies. So what it's saying is that if a group is not simple, in reality, the predictions on that are quite accurate by the network. It's around 95%, 96% accurate. But if the group is indeed simple, those accuracies are a bit lower. They are 83% in this case, right? And this matrix is called the confusion matrix, and it captures the number of examples of your simple class of examples or your non-simple class of examples which are correctly determined. So the key thing is that if you had a perfect outcome, you will only have non-zero elements appear on the diagonal, because then you would have predicted everything accurately. We're still working on the training set. On the test set, things might be even worse. So nonetheless, these are the class accuracies that we are concerned with. The higher, the better. Let's look at this validation set here, which again, to emphasize, by validation set, I do not mean what is technically a validation set here. I just mean the rest of the data set on which we'll apply our trained network, just to see how it does on unseen data. I made an error here because I should not have these extra features. Now it's checking only on 1,000 examples or so, rather over 2,500 examples. All right, let's measure the accuracies on the validation set. Turns out to be quite accurate, and turns out that it gets most of the outcomes correctly, but it misclassifies around 190 examples amongst this over 2,500 examples. So this is the learning outcome that we determined here. Are there any questions at this point? All right, if not, I'll continue. So let's go back and repeat this rather quickly for a different set of features. So we only looked at these features and the order parameter, but let's also include information about the group order. So presumably, if you had information about the group order or some other useful information, you might be able to better determine the outcome. So here, I wanted to go step by step on this, but I think we have to wrap up in about 15 minutes or so. So let's do that in one step. So here, I'll also include information about the resulting group being abelian or not, and I'll also include information about the order of the group. So I just included these two features. Let's generate the training set again. Let's use the same neural network, same activation. Let's train our network, and this will take 1 minute or so. Yeah. So one interesting way to see whether any learning is happening or not is through the learning curve, so which we can see in dynamic fashion here. The loss is being reduced. Now we know in full gradient descent, the loss will always reduce, but here we are stochastic. So therefore you might see some kinks, ups and downs. But it is not unusual that, especially in the context of pure mathematics, that you might have no learning at all. Try learning the Louisville function, which computes, whether a given integer has a odd or even number of prime numbers. And this is some example that Yang keeps mentioning. And this kind of hard classification problems are a good test bed for developing machine learning itself. So we have trained this network. We don't need this. Yes.
I know I just moved this, but now that I get it, I can ask you. So what you did now was to add more examples.
Not more examples. I included an extra property in each example. Rather.
Okay. So you were training till this 7, and now this 10 is property 10.
Yes, exactly. So I have included properties 3 and 10. So 3 is the property that the group is abelian or not, and 10 is the property that tells you what is the size of the resulting group.
Okay, great.
It seems to have done the computation. Did we do this already? Thanks for the question. Interestingly, in the context of pure mathematics, often you will see that only much less data is actually required, because there is already a lot of structure in mathematical data. You wouldn't expect as much structure in noisy real-world settings. So the pipelines of machine learning need to be rethought in the context of mathematical data. And there are the increasing number of examples of this. Let's check how we did on the training set. Okay, it did very well. It's this accuracy here, which is not a good metric, is still quite high. The good metric is here. So now you see that on this around 6,000 examples, it classifies most of the examples correctly. So in fact, it only gets around 40 of them wrong. So whenever a group is not simple, it's able to determine it with almost full accuracy. And when it is a simple group, again, the same outcome follows. Let's see how it did on the validation set, because that's the true measure of success. Because if, as I was explaining, that it's easy, accuracy is not a good metric. And testing on your training, training set is not a good measure of success. You need to test on unseen data. And again, I've made the same error by not including the 2 extra features. Apologies for my shoddy coding here. But now we're determining how well it did on the validation set or on unseen data. All right, okay. So again, it seems to have done exceptionally well here. So in fact, it has only got 11 out of more than 2,500 examples incorrectly. So this matches our expectation, presumably. You know, the more information we have about that might be relevant for the determination of the property of simplicity, the better our outcome might be. So in fact, it is not uncommon to have 100% accuracies here in the context of mathematical data. And you know, there are very, very many interesting examples one can talk about in that context. You know, we have looked at data related to again Calabi-Yau manifolds with potential applications to string phenomenology, and you know, data relating to bundles of line bundle sums over Calabi-Yau manifolds that help you with descriptions of quantum fields. And there are very many interesting properties of these bundles, such as stability. And they in those contexts, it's interesting to see the machine learning outcomes, and they can be extremely good. So before I go back to the slides, I'm going to pause here for a second to see if there are any questions. All right. So so what did we accomplish here? We went through this pipeline that we discussed in the last lecture, and we worked with we initially generated some mathematical data, which I did prior to this session, and we worked with that data to build a classifier for the mathematical property of determining simplicity. And some of the takeaways from here would be that the traces and the determinants of the generators seem to be an interesting determining factor for the property of simplicity in this context. And so one can work with all the other properties as well, or some other subsets of properties, and that will also be interesting. In fact, the initial exercise we had attempted with this was to just work with the matrix elements of the generators, and ask a neural network whether this is simple or not. And Max, who did all those experiments, had to deal with all these various pipelines, and he's a fantastic researcher. He helped us with building this pipeline, and there we were reporting much lower accuracies. So interestingly, some higher level properties here seem to be of more immediate utility in determining whether a group is simple or not. So I'm going to stop sharing this and share the mathematical insight we got from this exercise that we went through today, as well as the prior experiments that we did with Max. And I did not repeat those experiments here because training on such volumes of data is probably not a good idea in a time-limited setting. So I'm going to stop sharing here unless anyone has a question. All right. I'm going to go back to my slides. And wrap up rather quickly. So this is these are my collaborators we were mentioning, and this is one of the outcomes that we found. So as exemplified by the exercise we did today, these properties of determinants and traces seem to be important in the determination of simplicity of a group. And this is quite interesting. And when we found this insight, and this, interestingly, this insight only came because we were chatting with various machine learning PhD students and mathematicians about this problem. And it is actually rather hard to pinpoint how exactly we came at the result that I want to mention. But the process did involve domain experts. So I would always encourage you to do that whenever you're working at this interface. So nonetheless, the property, we were able to distill a very toy theorem, which I would believe is potentially a good exercise problem for an undergraduate or an advanced undergraduate mathematician or group theorist. Although the result depends on a few interesting non-trivial theorems about groups, but they are not immensely difficult to understand. So this toy theorem we found where some place some necessary conditions on these generators of finite simple yet non-abelian groups. So here the setting was, as I was describing earlier, that we have a two-generated subgroup of Sn, and we have two distinct generators, and they are not equal to the identity, because then it's effectively equal to having one generator. I failed to mention earlier that our generators are distinct, but they are. If the group, what we found and what the statement we can prove is, if H is a simple group, then the following must hold: that the permutation matrices that generate them must have a sign, must have a positive sign, and the traces, which is the slightly more non-trivial part to show, the traces of these matrices, we're talking about permutation representations, so it makes sense to talk about this in terms of the parameter n, although there are other finite simple groups, and there are broad classes of simple groups, as sporadic groups, groups of Lie type, etc. So what we found is that the trace of the generators must lie in this interesting lattice that we have. That the pairs of traces must lie in particular regions of this lattice that we have determined, and that's listed as number 2. And the reason is that if it is not, then we can show that it doesn't turn out to be a simple group. And I can share proof with you, or I can share our work with you if you're more curious. So effectively, through this machine learning exercise, we sort of ended up determining a new, we think is new, toy theorem for necessary conditions on generators of finite non-abelian simple groups. And this is exciting to us because this is the class of finite simple groups is quite fundamental in group theory, and also in various quantum field theories, and so this is rather exciting for us. On the right is this illustration of all these families of finite simple groups. So to sort of put today's session in the broader context again, we sort of talked about various things. We talked about how to pose interesting questions or conjectures by attempting to understand a theory around spaces that we posit, and we call them conjecture spaces. And we believe certain geometric or other properties of that space might be helpful in determining good conjectures or interesting conjectures. We looked at a very basic example of how to work with a machine learning model, and today we looked at how to It's sort of a different kind of an approach to generating new mathematical insights from data. A number of interesting, I haven't mentioned a number of interesting things, and one can go on, one can talk at other times, but there are various interesting tools available in interpretable AI to help with this process, and I can confirm that these are largely untapped in the mathematical community. And a simple example of this is relevance scores. So once you have a trained network and you tweak its inputs a little bit, and you can measure how sensitive your network is to that tweaking. So you can imagine that this is easily quantifiable, and it's a good proxy for the importance of this parameter in determining the mathematical property at hand. So as such, this is just an example of various other tools that are available and not fully explored. So with that, I'll finish my talk. Thank you.
Any questions? Yeah, there's a question here.
Out of this data set of simple groups, what kind of properties are learnable and what properties seem to be more difficult to learn for the algorithms?
Right. Thanks for the question. So it seems like in this case, most of the properties that we have explored, and which is a really small set, we have mostly been concerned with determining simplicity. It's learnable. It's learnable in the sense that you can determine with a coin flip. You can try to predict with a coin flip, whether a group is simple or not. But we definitely do better than that. And as we saw today, that it is the representations that you use, or the underlying properties that you are able to identify using your domain expertise is the important factor here. But I am certain that there will be various group theoretical properties that will be hard to determine here. Unfortunately, in this context, we have only looked at simplicity. We can query some other properties surrounding groups, but so far it seems that the kind of examples we have tried, we have learning outcomes, and depending on the representations we use, we can have poor outcomes, or we can have but still do better than a coin flip, or if we identify good features or good representations, then we can have very good outcomes.
And do you get any insights on sporadic groups?
So no, we are not claiming anything about that. We are working in a permutation representation. So whatever conclusions one can draw from this proposition, one is welcome. But some of the things we can do would be related to placing bounds on fixed point ratios of finite simple groups, which seem to be an important quantity. But we are not making any grand claims about sporadic groups here. But it would be interesting to discuss this result further at some point in the context of sporadic groups. I mean, they can still be two generated, and it will be difficult to work with a permutation representation of them, but it's not impossible. So all the representation invariant quantities that appear in this proposition and conclusions relating to that, relating to them, should be applicable to any finite simple group, which can be understood as a subgroup of Sn.
I have very question about, so you see that these tools that they are in Mathematica for your research, like for these neural networks, is this enough? Or you really think that one should also use maybe TensorFlow or PyTorch or so, if one really needs to solve some problem?
So, I think, I would respond to that by saying that if you tried, I mean, it's a question of style, perhaps, of how much time you might want to devote to your machine learning pipeline. But certainly it is true that you will have loads more handles on a different platform like PyTorch or TensorFlow. So, for example, in the audience is Damien, and we have played around on various problems with Mathematica, and often we have reached Mathematica's limits, and we've had to, quote unquote, graduate to other more standard forms or in industrial deployments of machine learning, but as you can see, I mean, the kind of result that we obtained here can easily be generated using insights from Mathematica, and there's lots of use both.
Okay, thank you.
I will make another point, is that usability is quite important here. I mean, in my experience, coming from the math-phys community, I'm used to good documentation, which Mathematica certainly does have. So what I do encourage my students, and whenever we need to we are reaching limits of Mathematica, and we are getting more serious about the machine learning pipeline, then we work with PyTorch or TensorFlow, and I assume it would be the same for you.
But for instance, for this problem that you were mentioning last week of determining studying the space of conjectures in certain domain, and
Yes.
and determining a metric, I mean, you had to divide by some equivalent action and determine a metric in that space. Is Mathematica enough to answer these kind of questions, or do you need something more? Oh.
Well, I mean, it depends on the kind of things you might want to do. So I think that Mathematica, in its current, if you're talking about the theoretical side of things, that's different. But Mathematica is quite fast. I promise Mathematica isn't paying me to advertise them. But I found them to be useful, and maybe some of it comes from background in doing symbolic computations in algebraic geometry, and there are amazing packages written out in Mathematica, and other incorporating other mathematical softwares like Singular or Sage, etc. One works. I mean, it really depends on the context of the problem. So if you're asking, the conjecture generation stuff, a la conjecture spaces, is good enough in Mathematica. Yes, absolutely, because if you think about some of the outcomes we obtained, they were outcomes that related to conjectures given by important mathematicians of the last century, and we were able to generate them without much domain expertise ourselves. So it really depends on what you're trying to do. I fully anticipate that in our pipeline, when things become even more interesting, when we scale up our pipelines, I would move away from packages which do not give me full flexibility or have huge computational overheads. So the choice should be dictated by the nature of your problem.
Question. I mean, so for example, in this problem that you just showed, so you were putting like 200, 500 neurons and stuff. So how you got to conclude that you need so many neurons in these internal layers? Is just by trial and error, or you have like some intuition if you first put the layer with many neurons and then less. So how you do this?
Yeah, so again, I mean, this was more of a demonstration, a full. So how how one could consider doing this, following a more appropriate pipeline, is by declaring a host of architectures. Let's say you consider all architectures with containing anything between 2 to 20 layers, and containing 10 to 1,000 or gazillion neurons, and all sorts of these hyperparameters, and you can build an entire class of architectures, and then you divide up your data set that you have generated into a training set, which can be a large portion of your data, a validation set, and a test set. So now what you can do is you sort of keep the test set away, and you train on, let's say you pick one architecture from your many different choices from the class of architectures you have declared. You train using that architecture on this training data, and you validate on the validation set. Your performance on the validation set is a good proxy for how your trained network will perform on unseen data that is on the test set. So by performing cross validation, you can get a measure for the performance of your specific architecture amongst the sea of architectures that you have declared. And you repeat this exercise for all your architectures, and you pick the one that gives you the best validation error. That's one way of choosing. There can be other approaches. There's differential architecture search and so on. But okay, you certainly want to have lots of parameters. Again, depends on the context of your problem. You might want to have a lot of parameters at play, because it seems like one of the strengths of neural architectures is it lifts your optimization problem to very high dimensions, where even if it finds local minima and not the global minima, which is pretty much always the case, you're still doing very well on unseen data. If you have a very small architecture, it might not be, it might not have the model capacity to explain your data in the first place. So this trade-off is effectively Occam's razor. So the choice of determination of your architecture is guided exactly by that. In other machine learning paradigms, such as Gaussian processes, the same thing is implemented directly using the loss function, using the marginal likelihood. So effectively one would keep Occam's razor in mind while determining the architecture. Here, one simple way of thinking about it that I used without following this full pipeline that I just described is that we have thousands of data points, and therefore we should have quite a few parameters.
Thank you very much.
Any other questions? So if not, Challenger, thanks very much for these very helpful and interesting lectures. Thanks a lot. Thank you.
Thank you for inviting me.